Good evening, everyone, and welcome to this lecture. We are into the concept of capacitance, and we are dealing with the capacitance. In the previous class, we had seen what do you mean by capacitance of an isolated conductor is the ability of this conductor to store electrostatic charge, or we can call it stores energy in the form of electric field. We had seen that the capacitance of an isolated conductor Q, charge on the conductor, is directly proportional to the potential. Q is equal to CV. This constant C is known as the capacitance of a conductor. We had seen its SI unit is farad. It's a scalar quantity. Farad is a very big unit. We had seen that the capacitance of Earth is around 711 microfarad. We had also seen the factors on which the capacitance of a conductor depends on size, shape, geometry, surrounding medium, and the presence of other conductors. We have seen that the capacitance does not depend on the value of charge Q, V, and the potential energy. We had seen also, sorry, the capacitance of a spherical conductor is 4 pi epsilon naught R. Yes or no? We had seen the potential energy of a capacitor. We have seen the energy density of electric field. All these small points we had seen, and in the last part we had seen the combination of spherical droplets. Do we remember these formulae? Yes or no? In today's
Yes,
class, we will move ahead and see the next part, and the next part is sharing of charges. So we'll write the heading sharing of charge of two conductors. What happens when two conductors are connected? Sharing of charges. Sharing of charges of two conductors. So write the heading. Okay, have you written the heading sharing of charges? Have you written the heading sharing of charges, beta? Now, what is going to happen in this sharing of charges? We are going to see two conductors, and these two conductors are going to be connected by a wire. Okay, so these two conductors are going to be connected by a wire, and initially we will see the charge, the capacitance, and voltage of the conductor. So how does the initial condition look like? The initial condition looks like this, which is coming on your screens now. Can you see it, bacha? That is the initial condition. You have two conductors which are connected, which are isolated, conductor number 1 and conductor number 2. The radius of conductor number 1 is R1, the radius of conductor number 2 is R2. Charge is Q1, C1, V1, U1. Q1 is the charge, C1 is the capacitance, V1 is the voltage, and U1 is the energy. Do we understand this? Yes or no? Do we understand this? Yes or no, beta?
yes, sir.
Okay. Okay, now what we are going to do, beta, is we are going to connect them. We are going to connect them by a conducting wire. We are going to connect them by a conducting wire. So now they are connected by a conducting wire. What you can see is the charge Q1 will change and it will become Q1 dash. Do you see this? Charge changes. The potential V1 becomes potential V. Basically, when you connect these two conductors, both of these conductors will come to the same potential V. Do we understand this? When
Yes,
you
sir.
connect two conductors, and we have written it in the note, they will connect. When you connect, they will come to the same potential V. The energy of the conductor will change. In the first case, the energy is U1. In the second case, energy is U1 dash. Do we understand this? Yes or no?
Yes, sir.
Okay. But one thing remains same. Capacitance C1. Capacitance still remains C1. Capacitance does not change. You can see for the second conductor, Q2 becomes Q2 dash. V2 becomes V, same potential. U2 becomes U2 dash, but one thing remains same. The capacitance does not change. Oops. The capacitance previously was C2. Now it is also C2. Do we understand this? Yes or no?
Yes, sir.
In the previous case, Q1 was C1 into V. Now this Q1 dash, the formula was written wrongly, is C1 into V. And similarly, your Q2 dash will be equal to C2 into V. So basically, values have changed, charges have changed, potential have changed. What they will ask you is what is the final charge on each capacitor and what is the final voltage. So these are the two formulae that you have to remember how this thing is achieved. So the first thing that you have to remember is the total charge remains constant. That means the total charge in the previous case was Q1 plus Q2. The total charge in the second case was Q1 dash and Q2 dash, that remain same. And the second thing that you have to remember is this. If you remember these two things, you will be able to find out all the things separately. I would want you to remember these things and also remember the formula. The ratio of Q1 dash and Q2 dash will always remain equal to R1 by R2 because it is C1V by C2V. C1 is constant, V is same. So Q1 dash by Q2 dash will become R1 by R2. Solving these two equations, bacha, you can get the value of Q2 dash and Q1 dash. So either you can remember the value of Q1 dash and Q2 dash, or you can derive the value of Q1 dash and Q2 dash. I will leave it to you how you want to remember it. I will give you all the possible iterations. So you can see this formula number 1 is the formula of Q1 dash in terms of Q. This is the formula of Q2 dash in terms of Q. What is Q here? Q is the total charge here. Do we understand this, bacha? So you can remember this formula, and then there is the formula for the common potential. So you can remember the formula of common potential also. I think it is easier to remember common potential. The formula number 3 for common potential is C1 V1 plus C2 V2 divided by C1 plus C2. The fourth formula is the formula for change in energy. Remember, the initial energy is always greater than the final energy. There is some energy which is always lost in the form of heat. This energy is lost in the form of heat. This energy is lost in the form of heat. The formula for this energy is given C1 C2 upon 2 times C1 plus C2 into V1 minus V2 square. I have seen a lot of questions come on this concept. If you can remember these formulae, you can understand how questions will be there. Have you noted down this formula, beta? The more you use this formula, the better you will become in using them. I'll give you a small question so that you can use them. Everyone ready?
Yes, sir.
I mean, whenever such a question comes, it might require some calculations. I hope you can do that calculation. I'll give you time for you to do that calculations. This is the question number 1. You are given two spheres of capacitance 3 microfarad and 5 microfarad are charged to 300 volt and 500 volt. When they are connected, you have to find out the energy loss. I hope you know how to find it out. I'll give you 2 minutes to calculate the value. So I have an answer, option C, and that is the correct answer. Well done. How are we supposed to do this? The question is very simple. You have to find the change in energy, and you can straight away apply the formula C1 C2 upon 2 times C1 plus C2 into V1. Oops. V1 minus V2 ka square. You can just put the values. Let me put the values for you. So change in energy 3 microfarad multiplied by 5 divided by 2 times 3 plus 5 multiplied by V1 square 500 minus 300 ka square. Remember, capacitance are in microfarad, so you have to multiply it by 10 raised to the power of minus 12. You calculate this, you will get the answer. The answer given is this one. I hope that is the correct answer. Everyone got this? Yes or no? Boys, girls, are we there? We got the answer, yes or no? Everyone got this? Okay, I will give you one more small question on this. I hope that all of you are able to do this one. In this question, you will have to apply everything to find out everything that is possible. So here is the question. Question number 2. There are two conductors given. They have just given it in a random shape. Doesn't matter. Shape doesn't matter. A and B are two isolated conductors that are large distance from each other. When they are joined by a conducting wire, find out the final charges. The initial charge and the capacitance is given. Can you see this? Yes or no?
Yes, sir.
You have to find out the final charges. You have to find out the heat produced. How will you find out the heat produced? It is the change in energy. Yes or no? And you have to find out the common potential. I will give you 2 minutes, 3 minutes to do this. If you can do this, that means this topic is logged and we can move forward. So you have 2 minutes to do this. So the first thing is to get the charges on each sphere or each conductor. How will I get the charges? I know Q1 dash. How will you find Q1 dash? Oh, the problem is you know the formula in terms of R1 and R2. You know the formula in terms of R1 and R2. You can convert this formula from R1 and R2. You can also convert it in terms of C1 and C2. In place of R2, plus put C2. And in place of R1 plus C1. So you can write this formula of Q2 dash as Q into C1, Q into C2 upon C1 plus C2. Similarly, you can write Q1 dash as Q into C1 upon C1 plus C2. You just multiply and divide by 4 pi epsilon naught and you will get your answer. So now I am going to do the same. So Q1 dash will be equal to total charge. How much is the total charge? Please 6 plus 3, 9. 9 into the capacitance of the first one is 3 divided by the total capacitance 3 plus 6. So your Q1 dash will become 3 microcoulomb. Your Q2 dash will be equal to total charge is 9 multiplied by capacitance is 6 divided by 3 plus 6. So this will become 6 microcoulomb. Do we understand this? Yes or no? We understand this? Yes or no? Do we understand this?
Yes, sir.
Okay, you can find the value of V1 here. The only formula we have done is Q is equal to CV. Q is given as 3 microcoulomb. Capacitance is given as Q1 is given as 6 microcoulomb. Capacitance is given as 3 microfarad. So divide 6 by 3. Voltage of this would be 2 volts and voltage of this will be half volts. 3 divided by 6. Do we understand this? Then you can put the formula of change in energy, which is heat given C1 C2 upon 2 times C1 plus C2 into V1 minus V2 whole square. Yes or no? No, yes. Okay. So I can put the values here. C1 C2 is 6 into 3 divided by 2. 6 plus 3 into V1 is 2 minus half square. Remember, your answer will come in microjoule. On the top, you have 2 microfarad divided by 1 microfarad. So 1 micro will get cancelled. Your answer will come in microjoules. And I think the answer in this case is coming as 9 by 4 microjoule. Anyone got this answer? Anyone got this answer? Anyone got this answer? Okay. That is the answer of heat lost in the energy lost in the form of heat. Then you have to find out the third thing. The third thing was finding out the common potential. Common potential is C1 V1 plus C2 V2 divided by C1 plus C2. Now this C1 V1 is nothing but Q1. So you can just write it as Q1 plus Q2 total charge divided by total capacitance. Total charge is 9 microcoulomb. Total capacitance is 9 microfarad. So this will become 1 volt. These are the different ways in which you can remember the formula. This question was just to make you understand the same concept. I will give you 2 minutes. If you want to note it down, please note it down. If you have any doubts, please ask. 2 minutes you have. So now we move ahead and write the next heading. Up till now, what we were dealing was a single conductor. A single conductor, and we had seen the capacitance of a single conductor. Now the next heading that we are going to write is known as a capacitor. A capacitor is the next heading. Is the next heading. Now what is a capacitor? Now basically a capacitor, sometimes it is known as a condenser. It consists of two conductors which are separated by each other by a small distance. Now this distance can be filled up with an insulator or a dielectric, or this space can be empty, free, vacuum. It could be filled with anything. So whenever you have a combination of two conductors which are placed at a small distance away from each other, this combination is known as a capacitor. So this combination of two conductors is known as a capacitor. One of the conductors is given a positive charge and the other conductor is given a negative charge. So one of the conductors, let me just cancel this out. Oops. So one of the conductors is given a positive charge plus Q and the other conductor is given a negative charge equal negative charge minus Q. The conductor which has given a positive charge is known as the positive plate, and the conductor which is given the negative charge is called negative plate. These conductors are known as the plate, and one is called as the positive plate and the other one is called as the negative plate. Do we understand this? Yes or no? Yes or no? Now, the charge on the positive plate of the conductor is known as the charge of the capacitor. As you can see, the net charge of the capacitor is 0, but we don't call the charge of the capacitor as 0, but the charge on the positive plate of the capacitor is known as the charge of the capacitor. Do we understand this? Okay. The potential of positive plate, let me call it VA or V positive or VA here. Let us call it VA, and let us call the potential of the plate, negative plate, as VB. So now I can write the charge Q is equal to C into VA minus VB. The charge Q will be C into VA minus VB. This charge Q is known as the charge of the capacitor. This C is the constant which is known as capacitance of the capacitor, and this V, which is the potential difference between the two plates, is known as the potential of the capacitor. So what has changed here? In case of a single conductor, we had Q is equal to CV because we had only one potential. In case of a capacitor, we have Q is equal to C into VA minus VB. VA minus VB is known as the potential of the capacitor. Now, instead of writing it the equation like this, we are going to write the equation like this: Q is equal to CV. We will not write VA minus VB. We will simply write it as Q is equal to CV. Now, whenever we write Q is equal to CV for a capacitor, you must understand Q is not the total charge. Q is the charge on the positive plate. Do we understand this? C is known as the capacitance of the capacitor, and V is not the potential of one plate, it is the potential difference between the two plates, which is known as the potential of the capacitor. Do we understand this? Everyone understands this, yes or no? The next thing is the potential energy or energy of a capacitor. Now remember, capacitor, now sometimes you will hear this term. What is a capacitor? Sometimes you will hear this term. Capacitor is a device. Capacitor is a device that stores. What does a capacitor stores? Capacitor is a device that stores what? That stores energy. So the most important thing that you must understand about the capacitor, obviously it consists of two plates, two conductors, one is positive, one is negative, Q is equal to CV. But you must also understand that every capacitor has, when I say capacitance of a capacitor, what do I mean by capacitance? Capacitance is the energy, is the ability to hold energy. Yes or no? Do we remember it? Do we understand this? Yes or no?
Yes, sir.
Capacitance of a capacitor is the ability of a capacitor to store energy. So it must store energy. So how does it store energy? It stores energy in the form of electric field. It stores energy in the form of electric field. And how much energy it stores? Well, you can write it as Q square by 2C, or you can write it as half CV square, or you can write it as half Q times V. This is how a capacitor की energy can be found out. Q square by 2C, as you can see, it's the same formula, or half CV square or half Q into V. Do we understand this? Yes or no?
Yes, sir.
Now, what is the symbol of a capacitor? The symbol of a capacitor will be two straight lines like this. One of them would be a positive plate, the other one might be the negative plate. So you can write plus or minus like this. Have you noted it down, bacha?
Yes, sir.
Now, when we talk about the types of capacitor, depending on the arrangement of plates and the shape of plates, you can have three types of capacitor. The first one is known as the parallel plate capacitor. The second one is known as the spherical capacitor. And the third one is known as cylindrical capacitor. It is based on their shape and arrangement of the plates. Based on the shape and the arrangement of the plates, there could be three types of capacitors. Have you noted it down, bacha? Have you noted it down?
Yes, sir.
Okay, you can write the small heading capacitance of a capacitor. It is the measure of its ability to store, either you can say charge, or nicely better way you can say, or to store energy. It is the ability of a capacitor to store charge or to store energy. Do we understand this? Yes or no? We understand this? Yes or no?
Yes, sir.
Now, what factors does capacitance of a capacitor depend on? There are three things. It depends on number one, the area of the plates. Instead of area, you can write the size, shape, or you can also write the geometry of the plates. If the plates are square, capacitance would be different. If the plates are triangular, capacitance would be different. If the plates are circular, capacitance would be different. If the plates are bigger, capacitance would be different. Do we understand this? Then it also depends on the distance between the plates. The plates are nearer, capacitance is more. If the plates are farther, we will see that in the next class. Third thing, it depends on the medium between the plates. If it is vacuum, capacitance is different. If it is any other medium, the capacitance is different. So these are the factors on which the capacitance depends on. Do we understand this? Yes or no? It is exactly same as what we had done for a single conductor. It depends on number one, size, shape, and geometry. Number two, the medium surrounding it. And number three was presence of other conductor. If you place another conductor, then the capacitance changes. And when you have two conductors, that combination is known as capacitor, and the capacitance depends on the distance between the two plates. Do we understand this?
Yes, sir.
Okay, well, that's it for today. We will move ahead in the next class and we will see the type of capacitors one by one and see what types of questions are supposed to come in your exam. So I'll see you in the next class tomorrow. Take care. Have a nice day. Bye bye, beta.
Bye, sir.
Everyone has noted this down? Okay, take care.